Start now.
Good morning, students. Welcome back to our States of Matter topic that is from intermediate first year, which is Unit 4. My name is Priyadarshini. So, so we are in the topic deduction of gas laws from kinetic gas equation. Okay, so we are relating, not we are relating this. Scientist has related all the gas laws to his kinetic gas equation, that is PV is equal to 1 by 3 mn c square. So it is like to prove all these gas laws are correct. Okay, so anyway, yesterday we have discussed about Boyle's law and Charles law derived or correlated with the kinetic gas equation. Okay, so now coming to Avogadro's law. Okay, we have discussed Avogadro's law also. So again, you can see here. Okay, so first for the first gas we are taking PV is equal to 1 by 3 m1 n1 c1 square. So first gas, so that's why we are mentioning m1 n1 c1 at a constant pressure and for a particular volume of gas. Okay, here all the gases, whatever the gas we take, we will take in a similar volume, container having similar volume. Okay, for the second gas we consider PV is equal to 1 by 3 m2 n2 c2 square. Okay, like this. So as m1 n1 c1 square is equal to m2 n2 c2 square according to kinetic gas equation, so we can equate n1 is equal to n2. Okay, and we have discussed this yesterday. Now coming to the Dalton's law of partial pressures, at constant temperature, total pressure of mixture of gases is equal to partial pressure of component gases. So that is Dalton's law of partial pressure. So according to Dalton's law, P1 is equal to P total P is equal to P1 plus P2. So here in kinetic gas, from kinetic gas equation, P1 is equal to 1 by 3 m1 n1 c1 square by V. So P, this V has taken this side. Okay, from this PV is equal to this equation. So V has been taken from here to here. Okay, so V has taken here. Now this is P1. Then what is P2? P2 will be 1 by 3 M2 N2 C2 square by V. So again I'm saying volume, for a particular volume we are discussing this. Okay, means the two gases are taken in a similar container having same volume. Okay, P2. Then P total pressure is equal to P1 plus P2. Just correlating, that's it. And it is proved right also. And conditions apply. Okay, at certain conditions and temperatures and temperatures only. So this is how you have to deduce the equations. Very simple, just correlate the kinetic gas equation with all the laws. So next, Graham's law of diffusion. So from this equation, so just rearrange the equation like this. So PV is equal to 1 by 3 mn c square. What is C, students? What is C? C is the root mean square velocity. Okay. M is the mass of the gas. N is the number of moles of gas. Okay. So C square is equal to 3 PV by Mn. Okay. This 1 by 3 Mn has taken to the left side of the equation. So now what is this? D is equal to mn by V. For 1 mole of gas it is considered density is equal to m by V. Density is equal to mass by volume. N is taken as 1. Suppose number of moles of gas is 1, density is equal to mass by volume. So see this m by V here, m by V. So it is reverse of density, so 1 by D we have to take. So 3p by D. Okay, why we have taken density in the denominator? Because this equation consider m by V is reverse here. M in the denominator, V in the numerator. So m by V is inversed here. So density is taken in the inverse place, that is in the denominator. So C is equal to square root of, where this C square is there, no? If you move the square to the right side of the equation, we have to write square root. So C is equal to square root of 3p by d. Now consider this. So particular pressure, at a particular pressure we are considering, no? That's why this pressure is constant here. So these 3 and p are constants here. So C is directly proportional to 1 by square root d, you can write. Okay. How it is correlated with Graham's law of diffusion? Graham's law of diffusion is R is directly proportional to 1 by D, or simply R is inversely proportional to the square root of density. What is, how you can relate R and C here? C. C means here, what is C? Velocity of the gas, velocity of the gas particles. So as I have said, velocities are, gas particles will have different velocities. We will take the mean velocity, root mean square velocity. Okay. So C is the velocity with which the gas particles are moving. Okay. Then according to Graham's law of diffusion, what is R? R is the rate of diffusion, means the velocity with which the gas particles move. Means simply volume of the gas moved or diffused in a unit time. Okay, if you apply Graham's law or correlate the Graham's law with a kinetic gas equation, then this C is considered as R, or R is considered as C. Means both are velocities only. R rate of diffusion and C both are velocities only. So C is inversely proportional to square root of density. So this is how the kinetic gas equation is correlated with this Graham's law of diffusion. Okay. So next topic is kinetic energy. I think kinetic energy is also deleted from your syllabus. Anyway, so from this equation, kinetic energy is equal to 1 by 2 mv square. Do you remember the kinetic energy equation? Kinetic energy is equal to half mv square. Is it similar or different, students? So this is the same thing. Half m, c is nothing but velocity only, v square. Then what about n? N is number of moles of gas. If n is equal to 1, if 1 mole of gas is taken, it is simply half mc square. But if n number of moles are taken, half mnc square. Okay. So we all know that for 1 mole of gas, PV is equal to RT. So PV is equal to 1 by mnc square according to kinetic gas equation. So if you rearrange the equation of this 1 by 3 mnc square, so by in multiplying and dividing by 2, you can write like this. Means 2 and 2, 2 in the numerator, 2 in the denominator. So then you can by rearranging the equation, so 2 by 3 into half you can write. Okay. So this half mnc square is nothing but kinetic energy. So this 2 by 3 is written here. So PV is equal to 2 by 3 ek. Ek is nothing but kinetic energy here. Okay, K is, it is not written like kinetic energy K dot E, it is written like E subscript K. Okay, so 2 by 3 is equal to RT. As PV is equal to RT, 2 by 3 is EK is equal to RT. So kinetic energy EK, K should be in the subscript form. Anyway, simply read it as kinetic energy. EK or kinetic energy is equal to 3 by 2 RT. Okay, so this is the kinetic energy for 1 mole of gas. Then you can rearrange this like ek by n is equal to 3 by 2 r by n t. Means we are multiplying n in the left side of equation as well as on the right side of the equation. Okay, that becomes 3 by 2, that is equal to 3 by 2 kt. Okay, then what is k? K here is K is equal to R by N, which is nothing but Boltzmann's constant. Okay, so K is equal to Boltzmann's constant, its value is 1.38 into 10 power minus 16 ergs per Kelvin per molecule. So this particular K value you have to remember. K is equal to Boltzmann constant, that you have to remember, students. N is Avogadro number of molecules. N is equal to Avogadro's constant, that is equal to how much? Wherever capital N you see, consider, in some cases, not everywhere. Mostly N is capital N is Avogadro's constant, that is equal to 6.023 into 10 power 23 molecules or particles or ions. Okay, whatever. If it is gas, gas particles. Then R is gas constant. Okay, then what is K? K is equal to R by N. Okay, so if even you forget all these equations of all these reduction, simply you remember K is equal to R by N anywhere. From this equation we have written here K is equal to R by N, but excluding this also you have to remember K is equal to R by N anywhere. So that is nothing but Boltzmann constant. These are the values for Boltzmann constant, and units are also important. So this can be asked as a 2 mark question, students. Okay. So coming to the behavior of real gases and deviation from ideal gas behavior. So already we have discussed in the gaseous state, where we have reduced that ideal gas equation. We have seen the differences between the real gas and the ideal gas. So as I have said, all the gases are real gases. Means whatever the equations that whatever the theories that we have seen, they are applied for ideal gases, means they are theoretical or hypothetical. So we are imagining the gas as ideal without intermolecular forces and all the kinetic the molecular theory postulates we have seen, no, all they are for ideal gases. Okay, then what are real gases? Real gases are the actual gases. Real gas behavior is the actual behavior of the gases uh, in this atmosphere. Okay, so real behavior is something hypothetical, but real gases can also approach the behavior of ideal gas at low pressures and high temperatures. So this is the condition, at low pressures and high temperatures. Okay, high temperatures means medium temperatures, not like zero, below zero, like that, above than that. So it is considered as high temperature only. So suppose if you see the plot here, so this is PV versus P plot. Okay, versus P plot means according to which law we have taken this plot. So this plot is taken according to Boyle's law only. So according to Boyle's law, P is inversely proportional to volume. Okay, P is this, you see this graph. P is inversely proportional to volume. Okay, pressure decreases, volume increases. So this is the actual graph for Boyle's law. But what we have taken here, PV versus P, means PV versus P means with increase in pressure, what happens to PV? With increase in pressure, what happens to PV? So according to Boyle's law, PV is equal to constant, isn't it? According to Boyle's law, PV is equal to constant. P inversely proportional to V. When you take when you take V on the left side, that should become constant. PV is equal to constant. P1 V1 is equal to P2 V2. We have written now. So PV is equal to constant. Means with increase in pressure, volume decreases. Okay, if you plot a graph taking PV versus P, with increase in pressure, PV becomes constant by decreasing volume. Understood? Even even if you take volume on the x-axis, the same thing happens. With increase in volume, if you increase volume, pressure decreases. Again, PV becomes constant. So that's why actually the graph should be like this. For an ideal gas, this should apply. Means PV versus P graph should be a straight line like this. See, okay, but actual gases, if you consider hydrogen, helium, carbon monoxide, and methane we have taken, so that is the scenario is completely different. So these lines, these PV versus P graphs are drawn for all these four gases. They are they are not exactly on the ideal gas line. They have deviated from the ideal gas line. Okay, so at constant temperature, PV versus P plot for real gases is not straight line. It is thus found that the real gases do not follow ideal gas equation perfectly under all conditions. So what happens to this line? You see, some gases are these totally four gases we have taken, but the four gases are having different types of uh, curves. So here hydrogen and helium are having positive deviation. Okay, if you get a line above this ideal gas line, it is said as positive deviation. If you get a curve below the ideal gas line, that is considered as negative deviation. Okay, H2 and He, helium and hydrogen, are both are having positive deviation from the beginning. But some gases are like that. Carbon monoxide and methane, say, they are deviated negatively, and at some point they are reaching ideal gas line, and they are again showing positive deviation, and at some point they are reaching a minimum point. Okay, like this, they are reaching a minimum point, and then they started showing positive deviation like this. So these deviations are purely based on the nature of the gas. Okay, these deviations are purely based on the nature of the gas. Every single gas they has its different curve, different deviation based on its nature. Okay, so this proves that all the gases that we consider, all the gases which we do experiments in our daily life are uh, real gases. They are not ideal gases. They deviate from the ideal behavior at different conditions, that is different temperatures and pressures. Okay, and even if you consider this plot, pressure versus volume plot, if you consider an ideal gas curve is like this. The red color one is the ideal gas curve. But see the real gas curve. At high pressures, at high pressures, the real gas is deviated from the ideal gas behavior much larger, large deviation. See the volume, if you plot the line, if you extrapolate the line like downwards, not extrapolation, just you note the volume here. At high pressures for the ideal gas the volume is low. At high pressures the real gas volume is high. Okay, if you draw a line like this, volume of ideal gas is lesser than volume of real gas, means there is a deviation from the ideal gas behavior. At which pressure? At which pressure? High pressure or low pressure? At high pressure you can clearly see the deviation like this. But when the pressure is decreased, as the pressure is decreased, the real gas approaches the ideal gas curve, means almost the same. Means at low pressures real gas do not deviate from the ideal behavior much. Okay, real gas approaches the ideal gas behavior. Understood, students? These plots are really important for your competitive exams. Many questions may be framed from these graphs. Okay, all the graphs that we consider as not important for IPE, these may not be asked for IPE, particularly to draw the graph or to uh, give the applications of these graphs. Okay, they may not be asked in the IPE, but all these are important. All the graphs are important for the competitive exams. But they are easy. If you understand it once, you can answer any question which is framed uh, from these graphs. Okay, so what the same thing taken here. Okay, for Boyle's law. We have drawn the line for the Boyle's law only in the last graph, and this graph is same. So if you draw the line downwards, the volume V1 is ideal gas volume is lesser than the real gas volume. Okay, so real gases show deviations from the ideal gas law because molecules interact with each other at very high pressures. So at very high pressures, molecular interactions start. So if you apply high pressure means here not the internal pressure of the gas, means not the pressure of the gas. High pressure means if you apply an external external pressure, if you suppose if you take a gas in a cylinder with a movable piston, if you compress the gas, imagine you compress the gas. Imagine the graph or picture that I have given in the Boyle's law. In the Boyle's last slide, I have given you a picture with a cylinder with movable piston. If you apply the pressure from upwards, then the gas compresses. It is nothing but the gas is at high pressure. So at that condition, what happens? The molecular interactions starts. Means as the gas particles are coming together, coming nearby, they are showing the molecular interaction starts. Okay, according to the laws what we have discussed, the molecular interactions are not present between the gas particles. This is assumed while deducing all while giving all the theories or laws, gas laws. What they have assumed, all the scientists have assumed that there is no interaction, there are no interaction between the gas particles. But this is not true at all the conditions. When the pressure is increased, particles come together, then um, molecular interactions start and attractive forces increases. So these do not match with the assumptions of the scientists. At high pressures, the molecules do not strike the walls of the container. Right, do not strike the walls of the container means they interact with each other. So each molecule is dragged by some other molecules that they do not easily strike the walls of the container. Okay, so this proves that there are molecular interactions. Thus at the high pressure exerted by the gas is lowered. Okay, this is a very important point. When the gas particles, when the pressure is applied, when the gas is compressed, the molecular interactions increased. Due to the molecular interactions, the particles of the gas cannot strike the walls of the container as earlier. Okay, so that's the pressure exerted by the gas is lower than the pressure exerted by the ideal gas. See earlier the gas particles when striking the walls of the container, they will exert some pressure on the container. Okay, so that is the gas pressure of the gas. But after compression, after applying external pressure, this pressure of the gas is decreased, means they do not strike the walls of the container as earlier. So thus this point, the pressure exerted by the gas is lower than the pressure exerted by the ideal gas. So that's why we will correct this this ideal gas equation with some correction term. Okay, so now the P ideal is equal to P real plus a n square by v square. Okay, so what is this actually? This is a correction term, means according to this point pressure exerted by the gas is lowered. So lowered means some value should be added to the real pressure to become equal to the ideal pressure. Okay, so if it has to, this real pressure of the gas has to become equal to the ideal pressure, some correction value has to be included in the ideal gas equation. So now we are going to change the ideal gas equation to suit it for the real gas equation, means real gas. So what we have seen that in the differences last point, ideal gas equation and real gas equation. So real gas equation is also called as van der Waals equation. So that van der Waals equation is going to be derived like this by correcting the ideal gas equation with some correction terms. So this is the correction term. This A is a constant which is based on the intermolecular forces of attractions when pressure is applied on the gas, and N is the number of moles and V is the volume. Okay, then repulsive forces also become significant when the gases particles are coming together. Along with the attractive forces, repulsive forces are also significant, that we have to remember. So the volume occupied by the gases molecules is also restricted to V minus NV. Volume is decreased. So simply imagine, when the gas is compressed, pressure is applied on the gaseous particles, volume decreases. So volume is restricted to V minus NB. So this NB is the correction term for the volume. So such how, if you consider both the pressure and volume corrections, the PV is equal to nRT will become P plus A N square by V into V minus NB is equal to nRT. So this equation is just similar to PV is equal to nRT, but this is a ideal gas equation, but this is a real gas equation. This real gas equation is called as van der Waals equation. So this is also a 2-mark question. What is van der Waals equation? Explain the terms in van der Waals equation. Okay, this A n square by V square is the correction term for pressure correction. Okay, pressure correction is based on the molecular attractions, and NB is the correction term for volume. Okay, so this A and B are called as van der Waals constant, and their behavior depends on purely on the characteristic. It is purely depends on the characteristics of the individual gases. Okay. So the same thing discussed here, what happens at the low temperature situations. Okay, in the last 2 slides we have discussed what happens in the high pressure situation. The same thing, almost the same thing happens if you decrease the temperature. Okay, intermolecular forces become significant, because when you decrease the temperature, kinetic energy of the molecules decreases, because see, when we have discussed the thermal energy, when you increase the temperature, thermal energy is increased, kinetic energy is increased, movement of the particles increased. So the solid will convert it to liquid, liquid will convert it to gaseous state. The same reverse condition, if you decrease the temperature, means if you decrease the thermal energy, intermolecular forces become significant, kinetic energy decreases. Okay, so the molecules can be captured by one another due to attractive forces. Okay, molecules travel with low average speed. When kinetic energy is decreased, their speed is also decreased, so the molecules can be captured, means dragged or attracted by each other. Okay, real gases show behavior when conditions of temperatures and pressures are such that intermolecular forces are practically negligible. This is the actual assumption by all the scientists. Okay, so that's why they have proposed it as an ideal gas. Okay, whatever the theories they have proposed, those theories are applicable for ideal gases. And when they have really done the experiments with the gases, these, whatever the graphs they have drawn for ideal gases, are not exactly coincided with the graphs drawn on experimental basis. You understood? So earlier they have taken some, they have assumed something and plotted the graphs. Okay, the curves we have seen, the Boyle's law, Charles law, all those curves. But after doing experiments exactly with the gases and plotted, those two graphs are not coincided. Little difference, little deviation is there, that we have discussed, like deviation from the ideal behavior. Okay, the real gases show ideal behavior when pressure approaches to zero. The same thing, real gases more like an ideal gas at the high temperatures and low pressures. Okay, so this is the low temperature condition. Simple, the same thing happens. Kinetic energy decreases, attractive forces increases. The same thing happens with the low temperature and high pressure situation. So this is the important point that you have to remember. Gas behaves more like an ideal gas at a high temperature and low pressure. High temperature and low pressure, remember. Okay, so here another term comes, the compressibility factor. Okay, so PV is equal to nRT can be written in terms of this compressibility factor. So deviation from the ideal gas behavior can also be measured in terms of compressibility factor Z. Okay, so Z is equal to PV by nRT. So if Z is 1, imagine Z is 1, PV is equal to nRT or not? That is nothing but ideal gas equation. PV is equal to nRT is ideal gas equation. But for ideal gas, N is equal to Z is equal to 1, compressibility factor is equal to 1. So PV is equal to nRT. So this becomes 1 for ideal gas. There is no compressibility factor, means there is no attraction, so that compression does not affect. Okay, Z we consider it as 1. For real gases, Z deviates from unity. At low pressures, Z is greater than 1. At high pressure, Z is less than 1. So if you if you want to include the volume of real gas and ideal gas, this is the condition. Z is equal to volume real by volume ideal. So these terms you have to remember. You can get a simple problem or 1 mark or 2 mark problem based on these equations. So if you include volume real and volume ideal, there is a simple derivation I have not included for this. Just remember Z is equal to V real by ideal. V means volume. Okay. So then up to what pressure these gases do not deviate, means at what pressures gases follow ideal gas behavior, at what pressures they will deviate from the ideal behavior. It is purely based on the nature of the gases. So all the gases do not deviate from the ideal behavior at a particular pressure or at a particular temperature. Based on the gas, the deviation changes. So the temperature at which the real gas obeys ideal gas law over an appreciable range of pressure is called as Boyle's temperature or boil point. Okay, so this is one of the 2 mark question. What is boil point or boil temperature? So this is the temperature at which real gas obeys ideal gas law. Okay, then above this temperature, above this temperature, the real gas deviate from the ideal gas behavior. Okay, these lines as it is, you can remember very easy. There is no much discussion in this. So boil points depends upon the nature of the gas. Above their boil points, real gases show positive deviation from ideality and Z values are greater than 1. Below boil's temperature, real gases show uh, negative deviation, the Z value will be lesser than 1. Okay. And again the same point, at low pressure and high temperatures, gases show ideal gas behavior. Okay. So students, these are the questions I want you people to write. Okay, so I think I have covered almost all the answers for these questions. I want you people to write notes for all these questions. Once go through the textbook first of all. So no question paper will deviate from the textbook. If it is deviated, then marks will be allotted for that, means out of the syllabus what you say. Okay, so reading textbooks is much important. Every question in even in competitive exam also will be given from textbook only, but difficult questions will be given in competitive exams, but the syllabus is the same, no? So basics for any competitive exam is uh, foundation will be laid from the textbook itself. First you read the textbook, every point you have to read. Don't first itself, don't go for the IPA exam pattern. Okay, don't read the answers for questions, IPA questions like that. First you start with the textbook, first you start with the introduction, first line itself. Okay, introduction will give you the overall idea of the topic. If you miss the introduction, definitely you will feel like it is something you are unknown about, or something you can't study. It is difficult you feel. Read the introduction also in your textbook. Okay, so I want you to write all the answers for these questions, like derive ideal gas equation from gas laws, explain Graham's law of diffusion, Dalton's law of partial pressure. See, reduce the Boyle's law, Charles' law, Graham's law, Dalton's law from kinetic gas equation, and derive an expression for kinetic energy of gas molecules. So this is there in one slide. The most important question: write the postulates of kinetic gas equation. Okay, and these, I think these rest are 2 mark questions. Explain different terms in van der Waals equation. Which gas diffuses fast? Okay, which gas diffuses fast? The rate of diffusion, application of rate of diffusion, this question. What are STP conditions? Values for gas constant in different units, this is there in one slide. So that is also very important question. Many number of times this question is asked. Even I think last year also this question I have seen in a question paper. Gas constant in different units, Boltzmann constant, and state Dalton's law of partial pressures. Okay, so this is also very important and very simple question. Dalton's law of partial pressure, very easiest question, and the application part is also easy. So some students feel that doing problems, some students, I have seen some students with answer papers, they will write all the theory part, but they miss the problems. They miss the problem. See, this question, Dalton's law of partial pressure, simply this problem is very easy problem. You can do this problem and you can apply in Dalton's law of partial pressure. The thing is, you have to read the problem twice. Okay, first read the problem twice. What is given in the question you write down first. Given that, okay, given that carbon dioxide, the weight of the carbon dioxide is 4.4 grams, the weight of the N2 is 5.6 grams. Okay, at which pressure it is given? 1.5 atmospheric pressure. Okay, the total pressure is given here. Understood? So this is in terms of mole fraction. This problem has to uh, calculate by calculating first the mole fraction. First, the number of moles you have to calculate. Means for carbon dioxide, you have to calculate number of moles 4.4 by 44. Molecular weight is 44, like that. So you can get the number of moles of N and N1 and N2. Then partial pressure of carbon dioxide is equal to mole fraction into total pressure, like that. That equation you have to take. It is very easy. You put it on paper, everything what you get in mind, you put it on paper, you can do anything. So some not some, all the liquid state is deleted from their new syllabus for this academic year. So I'm not discussing all those topics. Have just made some slides for this liquefaction of gases, liquid state. If you want, uh, these are not excluded for your from your competitive exam. Students, remember, all this exclusion of syllabus is for ITU only. For all the competitive exams, definitely you have to study all this. Okay, so these slides are there. You just go through these slides: liquefaction of gases and for liquid state. Okay, after this session you just pause the video and you can go through. So far what we have discussed. So far we have discussed about the states of matter, intermolecular forces, thermal energy, the gaseous state, gas laws, ideal gas equation. So density and molar mass in gaseous substance. Molar mass of a gaseous substance means density is included in the PV is equal to nRT equation. Then Dalton's law of partial pressure, Graham's law of diffusion, kinetic molecular theory of gases, and behavior of real gases, deviation from the ideal gas behavior. Okay, each particular topic is different anyway, interrelated, but very clear, very clear, very easy to study also. So this in this chapter you can easily score that 4 plus 2 marks. Okay, thank you students, thank you for watching. Again go through these slides, write the notes, derive the equations. Take 2 hours, you can complete this chapter. Just 2 hours you uh, put your time, you can complete this chapter. Thank you so much.
కంప్లీట్